Hello, and thanks for giving me the opportunity to talk with you today. I'm going to talk about a radio image mapping project, Polymetallic Rosebery mine in northwest Tasmania. Rosebery mine is located in the Cambrian-aged Mount Read volcanic belt in northwestern Tasmania. It's a polymetallic mine, and it's 100% owned by MMG. And today marks the 85th year of continuous mining and milling at Rosebery. It's a 3D model of the mine here, and we see that the ore body strikes to the north-northeast, and it dips 43 degrees to the east. It plunges to the north, and so at present state, the mine is about 3,000 meters long and has reached towards the north, had reached depth exceeding 1,500 meters. So it is now one of the longest and deepest mines that are currently in operation in Australia. If we look at a generic cross-section of the Rosebery geology looking north, we see that the mine is associated with volcanogenic massive sulfide deposits. It sits in a transitional stratified volcanoclastic sequence. It consists of sphalerite, galena, chalcopyrite, and electrum, and it's quite conductive from a geophysical point of view. It's also in places capped by a carbonaceous black mudstone known as the black slates, which is also quite conductive. The prospective sequence sits between the lower Rosebery fault and the upper Mount Black fault. The ore bodies themselves are individual lenses of sulfide ore, and they're named after the letters in the alphabet. And the deeper ones, the most recent ones, are WXYZ lenses, and they were discovered from step-out drilling. And specifically Z-lens, which we'll talk about today, is a poorly tested zone of mineralization that sits about half a kilometer to the north of the existing infrastructure at Rosebery. Z-lens was discovered by surface exploration drilling on two east-west sections. These sections here, and they have wide intersections of subgrade ore. And so the question is, have we missed the possibility of some higher grade ore sitting out where we have the indications of settling? And it was decided that radio image mapping may be a reasonable technology for trying to image the space between the already existing drill holes. Radio image mapping method relies on the absorption of radio frequency waves in a media at frequencies between 300 and 2,500 kilohertz. You can consider the radio waves to travel in straight line paths from transmitter to receiver. So if we consider here a transmitter with a specific emitting a radio signal at a specific frequency in one borehole, and a receiver moves up and down in a nearby receiver borehole, then it will record a received signal intensity that varies only with the distance to the transmitter if the media was homogeneous. However, if there's a conductor located in the area between the two drill holes, then we would see a localized reduction in received signal intensity due to the presence of this conductor. That's because there is an increased absorption of energy for when the radio path go through the conductor. So any shift in phase shift and reduction in amplitude, that's a function of the electrical conductivity distribution along the ray path in the traverse media. And so we can move the transmitter and the receiver positions about, and thus get a better understanding and a full tomographic survey of the material between in the plane between the two drill holes. and that data can then be first data processed, and then it can be imaged by straight ray attenuation tomographic imaging. For the survey at Rosebery, we chose to use the Russian FARA system, and it consists of a transmitter probe that is 42 millimeter in diameter, so that it can go into NQ holes or wider or larger. The transmitter is quite small; it's only 1.5 meter long, but it has an associated 50 meter antenna below it, and an associated 100 meter spatial filter booster array on top of it. So the top 100 meters cannot be measured, and the bottom 50 meters of the hole cannot be measured. And then it's connected by reference line over to the receiver hole, where the receiver is located, and the receiver and the transmitter can move up and down the holes independently of one another, controlled by the receiver surface unit. In a normal survey, you'd have maybe from 100 to 400 meters distance between the receiver and the transmitter hole, and the transmitter would be kept stationary, and the receiver would move up and down to sweep a fan spanning plus or minus 45 degrees. And then we'd move the transmitter 30 meters, and then we would repeat the sweep until we have done a complete tomographic survey for that transmitter receiver constellation. You then typically interchange the transmitter and receiver in the two holes and run a second tomographic survey. And so due to reciprocity, you would expect that the results from these two surveys to be identical. Any differences would be due to noise in the transmitter or the receivers. And so these reciprocal surveys provide an important quality control measure. And the final survey product would be an average of the tomograms that came out from these two reciprocal surveys. So it was decided to do a survey or a suite of surveys at the northern reaches of the Rosebery mine around Z-lengths. And this was done in April, May 2019. There were a total of 13 panels were produced. Each panel consists of two reciprocal surveys, so each panel took 2 days to produce. Surveying was only done in the part of the drill holes that were associated with the prospective zone between the Rosebery Fault and Mount Black Fault. We have here the results of these tomographic surveys. Blue, we see the high resistivity areas associated with the transitional volcanoclastic zone that hosts the mineralization, typically with resistivities above 2,000 ohm meters. Below the Rosebery Fault, there is a peritic volcanoclastic unit that's slightly more conductive, and so the Rosebery Fault is well reached. Not so with the Mount Black Fault, where there's no difference in conductivity, resistivity between the units on either side of the fault. The linear units that you see in the prospective zone between the two faults are typically associated with the conductive black slates, but hopefully also associated with mineralization. So following this work, MMG decided to do a number of follow-up drills to test some of the higher conductivity zones that have been identified between the existing drill holes from these radio image mapping surveys. And the first one we looked at is a section that spans between 503R and 504R B1, and this is the top of the section. This is the bottom of the section, and we're looking towards the south. So sorry, towards the northwest. And so you see here is the southwest, and here is the northeast. And we see that it's this zone of higher conductivity that's been imaged by the radio image mapping. Once a follow-up drill, 505 RD3 was put in place. It did, in fact, penetrate about 10 meters of black slate here at the top of this conductive anomaly. And towards the bottom of the conductive anomaly, it hits 12 meters of ore mineralization of about 4% zinc, 2% lead. Another intersection was done, or another follow-up drill was done in the section here between 402R and 405RD1. And we're looking here at the top of the section, and here's the bottom of the section, and we're looking to the north. So this is the western part, it's the eastern part, so that's west and that's east. And we see that on the radio image map, we have a conductivity session. And once we had the follow-up drill 505RD4, it did indeed penetrate a couple of meters of black slates before it hits 2 meters of high-level mineralization, 13% zinc and 7% lead and 11 grams of gold. So a nice intersection, just grade-wise, but just a bit thin on the on the thickness. So in summary, we'd say that within this highly resistant host, the conductive zones were effectively imaged by the transmitter and receiver drill holes up to 400 meters apart. And the intersections report, they do represent a technical success, but the geological context still remains somewhat ambiguous. There's not a direct representation between the response between the conductivity, the derived conductivities, and the mineralization grades that were inserted in the drill holes. It would have been nice to have done this in controlled circumstances within the mine, where we know there's massive sulfide mineralization, but unfortunately there was no ore lenses available with open drill holes for such a trial. But in conclusion, we would say that the drill holes, if they're provided in a, if they're well positioned and if they're in a resistive host, then RIM does offer a timely, efficient mapping of off-hole conductivity structures, and it actually opens up the possibility for drill targeting at depth across broadly spaced drill sections in a brownfields exploration setting. So just want to say thanks to the management of MMG for permission to publish this, and also thanks for the audience for listening here today. And I'll be happy to answer questions at the end of the session. Thank you very much.